Right. So, page. Right. So the last day, what we were talking about something called canonical correlation. And anytime you meet any term in statistics, or in fact in any other subject, you must always try to dissect the term, right? And see exactly what they are saying. So this word here, correlation, we know what this is, right? From our undergraduate courses, we know that this gives us um, a measure of the degree of linearity that exists between two variables, right? Let's call these variables x and y, right? And I know what, and everybody here knows exactly what I'm saying. So the process or the thought process and is this: if you plot two variables x and y, right, and they appear to be, linear, there appears to be some linear relationship between the variables. What that simply means is that it appears to be the best curve, or the best model appears to be a straight line model, right? Then the first thing before we do anything is we want to get a measure of how strong this correlation is. And when we use the word how strong the correlation is, what we are saying is that it means we want to get a measure of how close these points are, right, to the straight line. That's what that means in simple words, right? So what we normally do is we normally we use Pearson's correlation coefficient. And we know that R is between -1 and +1, right? So we have this. So this one here gives us the measure, right, of the linearity. So the closer it is to either +1 or -1, the stronger the Pearson's correlation coefficient, right? And the closer it is to 0, of course, the weaker it is, right? And in statistics, the only type of correlation that, so when you hear the word correlation, you should only think about a straight line correlation. You should only think linear. You should never think about, non-linear correlation. Now, in some instances, there exists that term non-linear correlation, but for this course, we are not looking at non-linear correlation. And in fact, all the correlations that we would be discussing in multivariate stats, and even all that you'd be discussing in the MSc in stats, would only be linear correlation, right? And these things are stepwise, meaning that the first thing is this, right? So you plot x versus y to get an idea of the relationship that exists between x and y, right? And if the points are close to this red line, then you know the correlation is strong, right? So working out Pearson's correlation coefficient here only makes sense if you know that, we have a linear relationship between x and y, some type of linear relationship. And after you assess the extent of the Pearson's correlation, right, what you want to do now is you really want to find out, what is this line of best fit, or how is y related to x. So the next step is really to is really to develop this equation here, to develop this, which is just the equation of a line, right? Right. So coming back now to this part here, so we know what correlation is, right? So we have an idea what that is. And now we are looking at the term canonical. Well, you could think about the terms canonical as being a new variable, right? So when you hear the term canonical, think about it as being a new variable, right? So, and it's similar to what we are doing. What we are doing in principal components, where we are actually finding some or creating some new variables, right? So the word canonical generally means acceptable, right? So let's see what we mean when we talk about, I'm going to put this in quotation mark, acceptable, right? Right. Now the underlying situation here is this, right? So you have two data sets. So this is what really happens. You have some data set here, right? Let's call this x1, x2, x3, x4, x5. And you have another data set across here, like this. Let's call this y1, y2, y3, y4, y5. The number of variables do not need to be the same, right? So I just making a little point here. The first point is that the number of variables in each data set need not be the same, right? So that's the first point. So across here we have 5 variables here, and on the right hand side we have 5. It so happens to have 5. I could put 10 on the right hand side, right? So I could have different number of variables. And the goal in this thing here, right? So the goal is to find out if there's some relationship. When we talk about relationship, we're talking about if there's some correlation between both sets of variables, right? So this is a research question. You want to find out that there's some relationship between both sets of variables, right? So that is our main issue. We want to find out if there is some relationship, and one of the ways to do that, right? Remember, correlation works with one variable and another one. It works with two variables alone, right? So one way to do it is to try to, find some new variables out of this set here, and find some new variables out of, or recreate or create some new variables out of that, in such a way that it will capture a large proportion. It's not to capture a large proportion, but it's to maximize the correlation between x1, between the first data set and the second data set. So let me just write down what I mean here. So what I'm basically doing Now I want to make sure I'm using the same notation because this the notation might be a little bit different. Okay, so you have it. Blank. Right. So I'll just use U and V. So U is this. So this is the first linear combination, right? So this is the U1 and U2 would be a 2, 1, and this goes down like this all the way up to U5. Like that, right? So because we have 5 variables, what we are doing is this: we are constructing. Think about when we did PCA, right? So think about it like that, but it's not the assumption is not relating to variances now, right? It's a little bit different, and I'll explain what I mean when I'm finished writing out the rest. So because because I only have 5 x variables, I am creating 5 linear combinations, U1, U2, U3 up to U5, all right? If I had 10, then I'd had U1, U2 all the way up to U10, all right? Okay, so now what I will do is I'll just put a little line here like that. And what I'm doing is I'm taking these variables now, the y's, right? And I'm doing the same thing. I'm creating some new linear combinations with the y's, right? So that's what I'm doing here. So let's call these linear combinations V, right? So V1, and let's, instead of A, we'll use B, right? So erase this, get this, right? So this is B11, B, oh, oops, X1 plus B12, X2 plus B, what? 15, X5. So this is Y1, sorry, this is V1 notation, right? Then B2, right? This is B21, X1. Oh, I said Y's, right? So this is Y. Remember, these are linear combination. The Y is not the X's. So this is Y1, Y2, Y5, Y1, Y2, Y, this is a Y, Y5. And then we go down to the, I'm just going to put dot, 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 like that, to the last one, V5. Right, so we have, so basically what we have so far is this. we have created new linear combinations of the x's, which I'm calling u's, and linear combinations of the y's, which I'm calling v's. All right. Okay. Now, what are the restrictions now? Now, remember when we did the PCA, we had some restrictions, right? So we said that um, the variance of y1 was greater than or equal to the variance of y2, and that is greater than or equal to the variance of y3, etc. So we had restrictions, and we had things like a prime 1, a1, that's 1, and we had a prime 1, say a2, and that was 0, right? So the question now is, what are the assumptions are we going to what assumptions are we going to build or put on these things, right? So, and these are some of the assumptions that we use. We're going to build these things such that the correlation between U1 and V1, let's call it lambda 1, is maximized. So that simply means these linear combinations, are made in such a way so that the correlation between these two, the first two, right? That is a maximum correlation that you could get. Then the correlation between the second pair, U2 and V2, say, let's call that lambda rho 2, is the second largest, right, correlation, right? So this is the first, this is the second, then you have third, fourth, etc. So what we are saying is that the correlation between U1 and V1 is greater than or equal to the correlation between U2 and V2, which is greater than or equal to the last one, correlation between U5 and V5, right? And one way you could think about, you could write it like this: rho 1 is greater than or equal to rho 2, which is greater than or equal to greater than or equal to the last one, which is rho 5, right? So we are creating these or getting these A's, right, and these B's, right, in such a way so that the correlation between U1 and V1 is the maximum. Then the second pair would be the second largest, and third pair would be third largest, etc. Right? So we have that. Not only that, we put some other restrictions that are very similar to the restrictions that we had when we did the principal component. So this is one set of restrictions, right? So and that concerns the correlations, right, of the canonical variates. And the second restrictions now is that the variance of any one of the U.I.s is equal to 1, and the variance of any one of the V, let's call them J's, is also equal to 1. So we assume that they have unit variance, right? So we have this for, of course, I is equal to 1, 2, 3, 4, and 5, because we have U1, U2, U3, U4, U5, right? And of course here J again is 1, 2, 3, 4, and 5. I'm just using different indices. I don't have to, right? So so what is telling me that if I take the variance of U1, it will be the variance of this part here and the variance of this is equal to 1, right? So that's what this is saying. Not only that, we have some more restrictions that are built in the formula, and these restrictions revolve around the correlations, right? So the restrictions revolve around the correlations. So the correlation between let's say I and UK is 0 for I not equal to K. All right, hold up, let's see what this means, right? This simply means that, let's take an example. The correlation between, say, U1 and U2, that is equal to 0 because 1 is not equal to 2, right? Right. The correlation between U1 and U3, that's 0 because 1 is not equal to 3, right? The correlation between U2 and U3, that is 0 because 2 is not equal to 3, right? So once these two indices here, the subscripts, yeah, once they are not equal, right, then the correlation is 0, right? So the correlation is 0. So that's one thing we have. And writing the correlation, writing this part here, the correlation of UI and UK is equal to 0, right? That's the same as writing the covariance of UI and UK is equal to 0, right? Why? Because, remember, recall the the correlation between UI and UK is equal to the covariance of UI and UK over the square root, right, of the variance of UI by the variance of UK, right? Okay. So if I tell you that the correlation, of UI UK is 0, of course I should put down I not equal to K to make sure that, they are not the same, right? If I tell you this is 0, then the only way, right? The only way this part here on the right hand side could be 0 is if the numerator across here is 0, right? So if you have, if you have 0 over square root of the variance of UI, variance of UK, right? To get the correlation to be 0, the numerator has to be 0. And if the numerator is 0, it means then that the covariance of UI and UK has to be 0, right? So we have an idea of what this, or why I should say, we have the covariance being equal to the correlation being equal to 0. Well, this is another restriction that we have, right? But this is only on the U's, but we need the same restriction on the V's. So I'm going to write the same thing down, but now instead of U's, I'm going to put V's. That's all. So I'm going to put down here. So that's number, what, 4? So the correlation between VI and VJ, say, is equal to 0 for I not equal to J. Right? Again, it has the same meaning that all the correlations between any pair of the V's, they are 0, right? They would be equal to 0. And well, this means if the correlation is 0, or VI and VJ is 0, this means that the covariance of VI and VJ is also equal to 0, right? Because in order to get the correlation to be 0, the numerator, which is the covariance term, has to be 0, right? So we have this fourth term, fourth condition, and we also have a fifth condition where we incorporate the U's and the V's, right? So the U's and the V's, so the covariance of UI and VJ is equal to the correlation between UI and VJ, which is 0. Right. So this is the last condition. So what does this condition mean? Well, this condition tells us that any of the UIs and any of the VJs, the covariance would be 0. All right. So let me write it down. I believe a few, so you'll have an idea what I'm talking about, right? So I'm just going to write this again, just quickly for you to get an idea of. And I'm going to put the V underneath, right? Like this. I keep on putting down the same X instead of Y. It's Y2, Y1, B, Y, Y, right? Right, so these are the first two canonical variates, right? And from this, what you know, or what we know so far, is that the correlation between U1 and V1, let's call it, say, rho 1, this is a maximum. Among what? Among all the correlations between UI and VI. Right? So it's a maximum for I is equal to 1 to 5. Right? So you'll have correlation between U1, V1, correlation between U2, V2, correlation between U3, V3, etc. And this one, the first one, will be the maximum correlation. That's what this is saying. And at the same time, let's get this one. Uh, and we also know, I should put this thing down here, that the variance of U1 is equal to the variance of V1, and that's 1, right? So that's one term that we know, one assumption that we make, right? And so that's it for this part, right? Now let's add a second pair now and see what is taking place now. So U2 now is equal to A 2 1 x1 A 2 x2 plus A 2 5 x5, right? And then V2 would be B, sorry, B 2 1 y1 plus B 2 2 y2 plus B 2 5 y5, right? So let's see, let's talk about, what are the characteristics here now, right? So some of the things that we do know about this second set of correlation, this second set of canonical variables, is that the correlation between U2 and V2 is the second largest one. Right? So that's the first thing that we know. So that the correlation between U2 and V2 is the second largest, right? So we have that. Now, what else do we know about the correlations or anything across here? Well, we could say something about the variances. The variance of U2 is the same as the variance of V2, and that is they are both equal to 1. So we know something about the variances. Now, what else do we know now? Because now, remember what we have, right? We have two sets of I nearly said principal components. We had two sets of pairs. We have two sets of pairs of canonical variates, U2, V2, which is this one in yellow down here. And we have this pair at the top here, right? V1, U1. Right, so we have those two. What do we want to say in addition to what we have so far? Well, this U2 that we have built up, right? This U2 and this U1, they must be independent of each other, right? So that means that the correlation would be 0. So one of the assumptions that we need to add is that the correlation to 10 is that the correlate to 10, right? So that the correlation between U1 and U2, that's equal to 0, right? So that means that this U1 and this U2 here, they are uncorrelated with each other, right? And we said that to say this, it's the same as saying that the covariance between U1 and U2 is 0, right? So the same thing. That's one thing that we are saying, but we also want to extend this now to the V's as well. So we're saying that V1 and V2, they are not correlated with each other. So I'm going to add that part here. So the correlation between let's put it like this, V1 and V2, that is 0. So this means that the covariance of V1 and V2 would be 0. Right, so we have that. Right, so we have this setup. Now we have these correlations, we have these covariances, right? Now, what are the other restrictions do we have? What other restrictions do we have? So we have restrictions. So far, we have restrictions on the V's. We have restrictions on the U's. We have another restriction on the variances, right? And we have a restriction, of course, on the correlation as well. But there's another restriction that we have, and this is the restriction. The restriction says that the which is actually itemized in number 5 here. It says that the correlation and or the covariance between UI and VJ, right? It's equal to 0. And of course, this is only valid, and I should always put this because this part is only valid when I is not equal to J, right? So when I is not equal to J, so that means I could be 1, but J cannot be 1, right? J has to be some other number like 2 or 4 or 6 or something like that. So this tells me, so if I'm just using the yellow covariates here, it tells me that U1, right, and V2, the covariance is 0, but it also tells me the covariance of V1 and U2 is equal to 0, right? So this tells me that the covariance or the correlation between U1 and V2, that's 0, and the covariance between U2, sorry, and V1 is also 0. So this is our next set of restrictions that we have here, right? So far, so just with 2 sets of canonical covariates, we have these, right? So let's just bring it together in a nice little in a nice condensed form and see what we have. So we have U1, U2, U3, U4, U5. Then you have V1, V2, V3, V4, V5. Right? So we have these two we have these 2 sets of variables. right? What you need to know, or what all these things were saying, all the conditions, is that this, if you choose this U, right, and you choose this V, you'll get a correlation. If you choose the second pair of U and V, you'll get a second correlation. If you choose the third pair, right, of U and V, you'll get a third correlation, right? If you choose the fourth pair, you'll get a correlation for those two. And if you choose the last one, of course, you'll get a correlation as well, right? So that's the first thing. So once the numbers are the same, the subscripts are the same, you will get a correlation that is not zero, right? Okay. So U1 and V1, the correlation is row 1, correlation between U2 and V2, it's row 2, etc. But these correlations are constructed, these correlations on the right-hand side here, the row 1 to row 5, they are constructed in such a way that row 1 is greater than or equal to row 2, and that's greater than or equal to row 3, is greater than or equal to row 4, this is greater than or equal to row 5. So they are in ascending order, right? Well, they are descending. The largest one is the first one, so it's descending. It's becoming smaller as you go along. Now, all the other assumptions that I made was this. The other assumption that I made, one was that the variance. So I made the thing that each one of the variants of the UI and the VIs is all 1. So the variance of U1 is 1, variance of V1, 1, variance of U3 is 1, variance of V3 is 1, etc. So all variances, they are all 1s, right? Okay. Now we come to a next step. Let's see. How should I do this? Right. Anytime now you cross them. So let's take U1 and V1. The covariance between U1 and V1, that's 0. The covariance between U1 and V3, 0. Covariance between U1, U4, 0. Covariance between U1, U5, 0. Right? So anytime you cross them, you get 0. That's all. Right? So, and not only that, the covariance between U1 and U2, 0. U1, U3, 0. U1, U4, 0. U1, U5, 0. Right? So what I'm saying is this: the correlations only exist, that is not non-zero, only where? On the horizontal, right? When these two indices are what? Are the same. So if this is 1, this is 1, the covariance is lambda 1. But once you change the indices, once the I is not equal to j, that means the subscripts are different, then you always get 0. That's basically it. Right. So this this is an extract from the textbook, so you could look at it. And so what you will notice in all the stats, and I think I said this already, but I'll just reiterate, is that that all the methods that we use are really imported from calculus, from linear algebra, and from optimization. That's basically it. So all the methods, they are methods that exist in these other fields, but we have found uses for it in different areas of statistics. So that's why it's being used, right? All right, so I'm going to drop down. Um, and when do you do a canonical correlation, right? A canonical correlation. When do you do it, right? Do you just take any set of two sets of variables and do it? And one of the things that you always do is you always try to have all the variables on the same scale, right? So that means if you have, you have variables like x1 is height and x2 is weight and so on, what you should do is you should try to scale those variables first before you actually do the canonical correlation. And sample size is always a big thing, and what you would always want is at least 10 subjects per variable. So that means that for each of the variables that you have, you should have 10 cases available there. So that is just to ensure that you have adequate power. Because remember what I said, I believe the last time I said hypothesis testing is a function, the results that you get from hypothesis testing is really a function of sample size, right? So if your sample size is pretty large, then you are more likely to reject H0, right? And if your sample size is pretty small, then you are more likely not to reject H0. Yes, it relies on the linearity, between these pairs. And I am not going to delve into the multivariate normal assumptions and things like that, because this part here only comes into the equation when we are doing hypothesis testing, right? So if we are doing hypothesis testing, of course, we assume that the data is normal because you can't do any tests without it, right? So the only reason why you know that z is equal to x bar minus this, the only reason you know that this has some no standard normal distribution with mean 0 and variance 1, the only reason for that is because initially you make some assumption. You always write something like that. Assume we have, say, a random sample. Let's say x1, x2, dot dot dot, xn from some normal distribution with mean mu and variance sigma squared, right? So we always make, so the reason why we could write this down is because of this. If we never made any assumptions on the data, we could never write this down, right? Unless we invoke the CLT, right, for large sample sizes. All right, so we have the iris data set, and in the iris data set, I believe some of you are working on it. What we have is we have different species. We have 3 species, right, of flowers, and what we do is we take 4 measurements on each flower. So so this is the species here, right, Setosa, and then you have 4 measurements on a flower. So they pick one of the flowers, right, from the species, and they made these measurements: sepal length, sepal width, petal length, petal width, and these are your 4 sets of measurements, right? So what we'll try to do, we'll try to perform a canonical correlation on that. Well, let's first do a box plot of the data and see what it looks like and things like that. And if you try to do a box plot of the data as is, what happens is that you'll notice sepal length is here. This one here is sepal width, and the reason why it didn't show up is because there was not enough space to write this thing out. And this is petal width here didn't show up as well, right? And this one is species. Now species, we said we had 3 species, right? Species 1, 2, and 3, and Setosa and 2 others. And when we did the box plot, we got this thing, we got this this box. Now, first of all, you don't do box plots with categorical verbal, so we should not have included this at all in the whole scheme of things. So that's why I am doing this now. I'm taking off um, that fifth column from the iris data set, and I'm calling this dot new. All right. So when I take off that fifth element, right, then this part disappears, and what I'll be left with, if I look at the first 10 rows of that new data set, you notice that species that was here is no longer here, right? So now I have my data in a way that I could go ahead and um, perform my canonical correlation. Now, I'm going to skip the long way, and in this class, you'll always see, sometimes you'll see in the R code, you'll see the long way and you see the short way. The long way is just for you to, gain a little confidence in actually being able to be a little more confident in using R, using some of the terms and so on, right? The code, like using terms such as scale to the apply function. So you see it, so you could apply it later on. But I'm going to drop down just because there's a simple way of doing things. Right. And this is a simple way that I'm thinking about. So there's this function called cancore in cancore in R, and what it does is the input really is 2 sets of variables. So what sepal dot measure is sepal length and sepal width. These two is what I'm calling sepal dot measure, and then petal measure is what I'm calling petal length and petal width. Right, so those are the 2 things that I have. So sepal length, sepal measures, petal measures, right? And now let's see what is taking place in this question. So in this question, what we have is, first of all, we have the correlations, right? So let's erase this part. Right. So these are the correlations, these 2 correlations. You might say, okay, so why do we have 2 correlations here, right? Now remember sepal, let's say the x's refer to this sepal measurements, right? Remember we have 2. We have sepal length, sepal width, right? So that means you'll have like a U1 is equal to A11x1 plus A12x2. And you'll have two canonical variables for sepal measure, right? E21x1 plus E22x2, right? So this is it for your sepal measures, your canonical correlations, right? And then what we have the Y's, and that I'll use the Y's to denote petal measures, right? So the Y's will denote petal measures. Remember, we have petal, we have Y1 and Y2. Y1 will be like petal length, and the other one will be petal width, right? So we'll have V1 is equal to B11Y1 plus B12Y2, and V2, which is B21Y1 plus B22Y2. Right, so we have these two canonical correlations. Now I just want to make sure, right? So those are the centers, right? Right. So let's look at the first correlation. So okay. So we have two pairs of canonical variables, right? So the first pair is U1 and V1, right? And the second pair is U2 and V2, right? What we're going to do is we're going to get the correlation of U1, V1, and that correlation here is the largest one, right, which is 0.9409, right? And then for this pair of correlation, the correlation between U2 and V2, between these two, between U2 and V2, and between U1 and V1, right? So what's the correlation between those two now? So those two, so the first pair of correlations is 0.909. So that's this one, right? And the second, the correlation of the second pair with the correlation between U2 and V2, right? So that will be 0.1, that's 0.1239, right? So we have our two correlations here. So what does this tell us? This tells us, there's a strong correlation between two data sets, right? Between sepal measures and petal measures, between those two sets of variables. That's what this here tells us. The next point that we will want to bring across is, we will want to test whether, that correlation is a significant correlation or not, right? Now, where are these A1s and these A2s, and where are these A1s and A2s showing up, in the output that we have here? Well, it's actually right here, right? So let's call this the sepal length. We call it that X1. Sepal width, we call it that X2, right? Petal length, let's call that Y1, and erase this. And this one across here. Sorry, this one, take this off. Right. So this is Y2. right? So now you're seeing exactly where these things are, right? All right, so let's see. So if somebody asks you, you know, write down for me the first canonical correlation for U1, right? What would it look like? Well, these are the coefficients here, right? So this is what you do. Take this off. So I'm going to replace now all these A's and B's with the actual numbers, right? So you'll see what I'm talking about. Okay. All right. Take this off as well. All right. So take this off. Right. Right. Kind of make this a little clean. Right. Take this. All right. So what you're doing in this case is this. You're simply writing. So this is U1 is minus 0.07. So, okay, so this is what I'll do. I'll just take the first two decimal places, right? Because it'll be kind of long for the rest, right? So I'll just take in the first two by x1. And then the second one is this one. So it's plus 0.03 by x2. And the second U2 now would be 0.04 x what x1 plus 0.08 x2. All right. All right. So right. So we erase this here like that. So so these are your first two canonical variates for U1 and U2, and I'll just write the ones for Y for V1 and V2 down here. You'll see 0.12 Y1 plus 0.04 Y2 minus 0.27, well, 28, let's say, Y1 plus 0.3 Y2 plus. Right, so you have, we have these two sets of variables here, right? Let's take this off. Right, so we have U1, U2, V1, V2, right? So we have those two sets of variables across here. And so this is what we know now, right? So we know the actual values for the A's and the B's. So the A's were here, right? Those were associated with the sepal lengths, right? X1 and X2, and the values for the B's were this set here, and those were the petal length. So this gives me I can write down my canonical correlation, variates, and I know the correlation. Next step is this. Okay, so that's good. I know the correlation. So what's the big deal? The next question is the correlation significant? That's the question you normally ask. Is the correlation significant? But before we jump into that, I just want to show you exactly. So if I plot, right, if I plot U1, right, and V1, right, because the correlation is 0.94, I should expect that all those points to be very, very close to a straight line, correct? So I'll just pull back on the last slide and I'll give you an idea. So what this is actually plotting the correlations between U1 and V1, right? And you could actually see here that it's not perfect, but there is some sort of linear correlation here. And it so happens that the correlation between U1 and V1 happens to be 0.94, so which is pretty high, right? But remember what I said when but let's plot the second pair now of correlations, right? So when you plot the second pair of correlations now, U2 and V2, you see what happens. You get something like a ball of points, right? So anytime you have something, anytime you see a diagram, right, that looks like a circle, right, and you have points all over the circle like that, then it means that you have a very weak correlation, right? So, and the correlation that we have here is 0.12. So um, what does this tell me, or what does this mean? Well, this tells me, you know what? If I run this code, right, and I get this information like this, then most likely when I do the hypothesis testing, the first one is going to be significant. The correlation between V1 and U1 is going to be significant correlation. But when I do the hypothesis test for U2 and V2, it's not going to be significant, right? Right. So this part here in the output is not needed, and all this part here does is gets the center of the each one of the variables. So it gets the center of each one of the variables, or the mean, or if you want, or the middle of each one of those variables. And the reason why these numbers are so small is because the data was standardized before doing it. Right. So this part now we come to we ask the questions: are the correlations significant? Right. So that's the question we ask ourselves: are the correlations significant? So we had two correlations, and we want to find out if they are significant or not. Now I have this bunch of output here, but I came across a really nice set or command in R that I'll jump the gun and just go straight into it. I think I have it. Right, I have it here. Right, good. And the other ways of testing, right? So that's good. Right. So this is one way that you could test the correlations is significant or not. So what you'll have to do is you'll have to construct a test statistic using the degrees of freedom and things like that. But I have an easier method later on, which is more straightforward. And what it gives you is it gives you this p-value, right? And the first thing is this: when you have a p-value, the first question you should ask is, okay, so what are the hypotheses being tested, right? So that's the first question we ask: what are the hypotheses that are being tested, right? And we know that it's significant because the p-value is really small and it's less than 0.05. So we know we have to reject 80, right? So let's find out. So it so happens that the hypothesis being tested is made up of two pieces. So it says that 80 is that the correlation between U1 and V1 is 0, and the correlation between U2 and V2 is 0. So it's saying that both correlations are 0, and each one is, of course, not 80. You know, when people use the term not 80, I use that term sometimes to simplify a whole host of different possibilities that you could end up with. So when I say not 80, right, I mean that U1 and V1 could not be 0, and uh, the correlation between U2 and V2 could be 0, or U1 and V1 are significant, not 0, and also the correlation between U2 and V2, it's not 0, right? So this is what this not 80 here, this not 80 really means all that, right? So it means this, or it means this, right? So when you reject 80, these are two alternatives that are possible. So now you have to decide, which one is the right alternative, right? So row 1, of course, we know row U1, V1 is the population correlation coefficient between U1 and V1, and row U2, V2 is the population correlation coefficient between U2 and V2, right? So far, what we know is that, okay, our p-value is pretty small, all right? So it's less than 0, so we have to reject 80. So we reject 80. We are saying, okay, so which one of these things is possible now, right? So we have to find out which one is possible. So the p-value, I said, is less than 0.05. We reject 80. This means that any one of these two things are possible. So the next question is, of course, to determine, which one of these is possible. And the only way you could determine that is by looking at what is different between those two. This and this is the same. However, this is equal, this is not equal. So it makes sense that, all you have to do is somehow determine the p-value that will test whether the second correlation is significant or not. So this is where the second p-value comes in the next slide, right? And the p-value here for that second test is 0.13, right? So that tells me, now what is that p-value testing? Is testing whether the correlation in U2 and V2 is 0 versus it's not 0. And the p-value is greater than 0.05, so that we do not reject 80. So that means we are saying this is good, right? So what's our conclusion at the end of the day, right? So at the end of the day, we have found that the correlation between U1 and V1 is significant. When we say something is significant, we mean significantly different from 0, right? That's what that word means. And the other one, rho U2 V2, is not significant, right? Okay, so let me get that question. Using these hypothesis tests, would you be able to figure out which canonical pairs are deemed necessary for your question? Yeah, you'll be able to find out which pairs are significant. Yeah. So you'll be able to find out which pairs are significant. Let me get back on this. Right. Right. So now, question: if you had a canonical correlation, right, and you had a bigger data set. So when I say you had a bigger data set, you had x1, x2, x3, x4. So you had 4 x variables, and you had say 4 y variables, y1, y2, y3, y4. Of course, you could have more, but you could only have comparisons for 4, because if you have 4 variables here and you have 10 across here, then you only have 4 pairs that you could compare, right? So in this case here, we have 4 canonical pairs, right? So you have U1 V1, U2 V2, U3 V3, and U4 V4. So in this case, how many p-values do you need to determine whether the correlations are significant or not, right? And what are the corresponding p-values that you would need? So on the first go, right, the 80, on the first one, it's U1 V1 equal to 0, and correlation between U2 V2 equal to 0, and correlation between U3 V3 0, and the correlation between U4 V4 is 0. Right? So that's H1, and H0, sorry, and H1 is not HO. Right? So your first p-value will test this, this pair of hypotheses. Then you remember, okay, so not HO now becomes a little bit, different, right? So not HO means that one could be significant and all the others may not be significant, and so on. So you have many possibilities here. Right. So one of the ways that you could actually do the hypothesis testing in a really nice, fast, efficient way, right, is to install the set of packages that I have here, these libraries here. And what I do is I install the packages, and the canonical correlation here is just CC. Right? Canonical correlation is a function after you install them, and we are doing it on the same 2 sets of variables, right? Sepal measures, petal measures. So you only have two sets of variables. You have 2 variables in each set of variables, and you store the output in CC1, and then you just call CC1 and see, the output, what you get. Again, the correlations come out easy, right? So no problems with the correlation. And it gives you a lot more than what you bargained for in terms of it really gives you like the correlations between x1 and x2 and so on. So let's call this, I believe we call this x1. Let's call this x2. Let's call this x3. No, I believe we're calling this y1. Y1 and Y2. And this one is X1, X2, Y1, Y2, right? So what it gives you, you could get this nice covariance matrix, and it gives you the breakdown of the covariance structure in the data. So it basically lumps or pulls all the data in both sets of variables together, right, into one covariance matrix. And you could take a look at the covariance structure, and it also gives you these get this a little bigger. This is the output here, and this one across here. And what these two gives you, it gives you the coefficients of the U1 and V1, right? So these are my U1, U2, V1, V2, right? But when you read these numbers here, you'll be able to replace these A1s, A12, B11, etc. with actual numbers, right? And yeah, we just replace them, and that's it. So you'll be able to see it. Uh, uh, what do we know about these correlations so far? Well, from what we said so far, we said that the covariance between uh, U1 and U2 should be 0. We said the covariance, sorry, between U1, V1 and V2 should be 0. We said that the covariance between U1 and V2 should be 0. And the covariance between V1 and V2 should be 0. So we know these, right? We know that. So let's try to prove one. So I just try to prove one and you know, see how things go. And so if you want to get, say, the covariance between U1 and V2, so this is U1 here. This is U1 here. And this is V2 here. All right, so erase this here. All right. So let's see. Right. So if you want to get the covariance between U1 and V2, what I will simply do is replace U1 with what I see up here, right? So that's what I'm doing here. And replace V2 with this down, with that here. So that's this piece here. And just work the covariances and see what happens. And somehow when you plug in the covariances, you're supposed to get 0. Now, where are you getting all those covariances between x1, y1, and things like that? Well, on the previous page, we had this covariance matrix here that we have, and this here will give you all your covariance between x1, y1, etc. Right? Just by looking at the appropriate term in the covariance matrix, and you'll be able to get all those terms, put them together, right? And you'll get your it will work out to 0. One of the things that you also get with this output that I think is really nice is that you get the scores, right? Now you might say, okay, so what do you mean you get the scores? You get the scores for the principal components, right? So, sorry, for the canonical covariates. So you get these 50 scores here, and you get the 50 scores for U1 and V1. U2, you could get the 50 scores for U2 and V2, etc. And you could you could plot them and you know, see if there's some strong relationship between them. You know, produce a visual and so on. So these are the 150 scores for the, let's call them V1 and say V2. And these are the 150 scores for the U1 and U2. So now you have these numbers. You could plot them. You could, you know, you could create your scatter plots. You could get correlations. You know, you could see exactly what it is. All right. So these now give you a little bit more, gives a little bit more detail, because this one here is a correlation, is a covariance matrix. No, it's a correlation matrix, but it's not the ones that we are accustomed with, because it's going to change, right? So this one here is giving us sepal length. It's x1, sepal width, that's x2. And this first one is your x scores as U1, and this one here is U2. So it's not a conventional correlation matrix that you would expect, where, you know, on the leading diagonals all ones, and then you have uh, you have the correlations here and here and symmetric and so on. It's not like that. It's a little bit different. You see, sometimes when people write programs, the output that they produce is sometimes a little bit unusual. So this value here that we have down here, this minus 0.929, this is the correlation between x1 and u1. So it's the correlation between x1, which is sepal length, and u1, which is the linear combination of x1 and x2, which is a canonical correlation, right? And the same way we create, we have a correlation matrix for y1 and y2 with this v1 and v2, and you have this correlation, right? And you have, I mean, you have all the possibilities. So you could just look at this and you could get all the different possible correlations that you might want from it. So in these things here, one of the one of the formulas that we will use in working out the covariance and things like that. I'm just going to put BYC X plus DY, right? So as AB covariance of XY plus AC, sorry, erase this. I think some people were having a little problem with questions like these. So you normally take this term, the first term and the first term here. So you go to AC, take the numbers out and put covariance of XX, like that. Now the covariance of X and X is just the variance of X, right? So, and then you go the same term again. So AD, the covariance now of XY. So you go to the second term with the first term, and you keep on doing that. Now with this term and this, then this term and that, and that's how you write out the formula extended, right? Right. So in this setup here, you also get the correlations that we have, and what we also have now is the p-values that we need. So the good thing about it is, in this set of libraries that we have in R, we don't have to worry about, you know, any situation at all, because all the p-values are given here and here. So the first one is testing whether the correlation between U1 and V1 is 0, and the correlation between U2 and V2 is 0, versus H1 not H0. So this p-value here tells you to reject H0. So we know it's not H0, right? Now what is not H0? It's not H0 simply means that the correlation between U1, V1 is significant, and U2, V2 is significant, or U1, V1 is significant, and the correlation between U2, V2 is not significant, right? So the only difference here is that is telling us is in the second correlation here. So, right? So this p-value here is going to test basically whether the second U2, V2, if it's 0 or if it's not 0. And the p-value is 0.13, so you don't reject 80. So the first correlation, this one here is significant, but the second one it's not significant, right? So that's canonical correlations, right? Anybody has any questions with anything?